Hello physics students. In this video, we're going to analyze the motion caused by inductive forces. So what's going to happen is it's going to be a mixture of our electricity and magnetism and mechanics. So the topic for today, motion caused by induction. We have this rail system here that we saw in the previous video, a resistor here, a magnetic field going into the board, and this bar is sliding. So we already analyzed this. But what I want you to do is, just for review, I'm going to create a pause, and what I want you to do is figure out the direction of the current in this bar in the pause. So your choices are obviously up or down, so go ahead and practice that now. All right, so here's what you should have said, you should have done. You should have said, well, as this bar slides, we're gaining more and more flux in this loop created between the resistor, the rail, and the bar, like this rectangle. As we move here, we're going to capture more of that flux. So we have to, Lenz's law says that there will be a current such that there will be an induced magnetic field that opposes this gain of B into the board, which means that B induced will be coming out of the board. B induced. And then what we do, once we find the direction of that magnetic field, is we use the right-hand rule between current and magnetic field to figure out the direction of the current. So the magnetic field comes out of the center of this loop here, and we see that at the bottom rail, my thumb points to the right, so the current goes like this and up through the bar. Now what I'm going to do is create another pause, and what I want you to do in that pause is to figure out the direction of the force on this bar. So go ahead and do that now. Okay, here's what you would do. You would put your index finger in the direction, so you use this right-hand rule, by the way, not this one, but this one. So you put your index finger in the direction of the current, and then our three fingers in the direction of the external magnetic field, which is into the board. So we swivel like this, and we see that our three fingers now point down, current this way, and our thumb points backwards. So there is the force magnetic. And remember, I said in the last video, you didn't even need to do all this. You would just know from energy considerations that as heat is being made in this resistor, that heat has to come from somewhere. It has to come from the kinetic energy of the bar, which means the bar has to lose kinetic energy, which means we need a backwards force. So you could just have put a backward force right from the start, and that's acceptable because you are using physics, the law of conservation of energy. So what we want to do to analyze the motion, what we're going to have to do is figure out the forces so we can figure out the acceleration. So the force we figure out, like we did in the last video, first the voltage produced, the mth from Faraday's law. You could derive this BLV. I'm not going to because we have enough notes for today. But there it is, the voltage of created by this bar. The current in this loop, assuming that there's no resistance in any other part except for this, or in other words, the resistance of these rails and the bar is negligible, then the current will be just from Ohm's law, voltage over resistance, this voltage over the resistor over there. And then finally the current we could find from ILB sine theta, the basic expression for the magnetic force on a current carrying wire in a magnetic field. So the current, we take this whole expression, plug it in here, then we have the LB, and then the sine 90, I ran out of room, so I just left it off because it's 1. And then just combining everything, we get to this expression. So that's the force that causes a deceleration. Now here's the thing though, it depends on the velocity. So the force will not be constant as this is slowing down. If the force was constant, then the deceleration would be constant, and the velocity graph would be a straight line down until it hits 0, and we would be able to solve everything with algebra. But what happens is that in the beginning, when this bar is moving the fastest, the force slowing this bar down is the greatest in the beginning, which means the deceleration of the bar is greatest. If this were a velocity graph, the velocity graph goes steepest in the beginning. And then at some later time, as we lose velocity, we have less deceleration. So the graph is not as steep. And then we have even less deceleration because the force gets smaller. Less deceleration. So we have this curve that comes down and approaches velocity 0 as we go through time. That's an exponential decay. And you might remember that in mechanics last year, What that meant is we had to set up a differential equation to solve that problem. Now, we've done several differential equation applications in this course this year with capacitors charging, discharging, inductors increasing their current. Oh no, we haven't gotten to that yet. Sorry. That's coming in the future. You don't know what an inductor is. But we've practiced it several times already. So what I want you to do is, as a review, remember, there were 4 main signposts that I asked you to memorize when we were deriving the equations for capacitors to help guide your derivation, which can be quite lengthy. What I'm going to do is create another pause to allow you in your mind, see in the pause if you could think of those 4 main steps in the derivation. Go ahead and do that now. Okay, what you should have said is, the first thing is you need to make a differential equation with the loop rule. That was for circuits, but what we did in mechanics is we made a differential equation using Newton's second law, A equals F net over M. The rest of the process was the same. Once we had a differential equation, we separated the variables, meaning we got all one variable on one side, all on the other. Then we integrated both sides, and then we solved for whatever we were after, either the charge or the current or the velocity. So make a differential equation, separate the variables, integrate both sides, and solve for what you're after. That's the same process as I said. So, I didn't think I created a pause for you to copy this down, so go ahead and do that now. Okay, so moving on. So we first make a differential equation, step 1, using Newton's second law, A equals F net over M. And then we realize that this is actually a derivative, the derivative velocity with respect to time. So now we have a differential equation, an equation that defines what a derivative is. We put this force in the numerator, and we put a minus sign because it's in the backwards direction, opposite of the velocity, or I should say opposite velocity. And then we divide by mass, and then I'm going to combine all this into just one fraction like this. So that's step 1. We made a differential equation. Here it is. Step 2. We separate the variables. And the way we could achieve that is we could divide both sides by v, so we have dv over v on this side, and I left a space here for a reason, and a space here for a reason. So all that's left are these terms without the velocity, and then I move the dt to the other side to join these other terms. So I separated the variables. All velocity over here, all time over here, and constants could be wherever they want, but the time and the velocities are separate. Step 3, integrate both sides. So that's why I left those spaces so I can put my integral signs. This, of course, began at v0, so I'm going to put v0 here. And it's going to end at some final speed. All right, eventually it'll stop at 0 when the bar comes to rest. But we want to find not the ultimate final speed, but some final speed, in other words, later after some amount of time has gone by. And then we integrate with respect to time. Our experiment began at time 0, and we are investigating at some other time t final. The left side just integrates to the natural log. So dv over v, ln v, and then of course we've got our limits here. And then this is a nice simple integral. dt integrates to t. Of course, all the constants are still there. And our limit 0 to t final. So we integrated both sides. That was step 3 and step 4. We plug in the limits and solve. So we plug in ln v final, ln v 0, and then t final minus 0. We could combine the two natural logs like this. And I dropped the little notation t final, just make it a little more simple looking. And then now we're again solving for v final. The way we can solve for v final, we got to get rid of the natural log. So we'll put this whole function into the exponential function, and the exponential of the ln just basically gives us the v final over v0. But the exponential on this side, of course, survives. Oh, I forgot to create a pause again. So let me create a pause to allow you to copy this down. Okay, so again, we did the exponential, and then we just moved the v0, and there's our expression, just how we reasoned out an exponential decay. We could graph it starting at v0 and going down to 0 as time goes to infinity. All right, so let me create yet another pause to allow you to copy this down. All right, so that was case, oh, I forgot to label it case 1. All right, well, we're going to have to squeeze this in here. Case 1. Okay. That was the case where we projected this bar and we just let the magnetic force bring the object to rest, and we did our differential equations and solved. The next case, case 2, is where we have some forward force pulling this from rest and accelerating it, speeding it up. Most commonly, it's a gravity problem, a bar falling. So let me sketch that so you could see what I'm talking about. By the way, you know, I just thought maybe to speed these notes up, I had an idea. I'm going to use what I've been calling my time machine. More generally, it's called a time delinearizer. And what it does is, as you know, I was doing some time travel and creating discontinuities in time. So that was fun. I could go from this moment to any other moment I wanted with this device. But what it could also do is speed up time and slow down time. So to speed up these notes, what I'm going to do is aim this at me and hit a button to speed up time so I could quickly write this whole solution out and you don't have to wait for me, and then I'll explain in a minute. So here we go. I'm going to speed up time on my body. Okay, so that was exciting. You probably saw everything sped up because I sped myself up. But here's a little interesting thing before I go on to the physics. While I was copying the notes, the time didn't feel any differently for me, because when I apply the time delinearizer everywhere to my body equally, everything slows down. Everything speeds up. My heart rate speeds up. My metabolism speeds up. But so does my brain. So there's no discontinuity. So for me, it just felt like normal time. But when I looked out the window during the solution, I saw a bird fly by, and it flew by as if it were just a snail in the sky. Because for me, time was appearing to be normal, which meant the world seemed slow to me. You seem slow to me. So it's a fascinating thing. Did the time delinearizer speed up time for my body, or did it slow down time for the whole universe? Interesting. If you're interested in a question like that, Albert Einstein had an answer. So you might want to look up time and the nonlinear nature of time and what Albert Einstein said about that with his theories. He did actually say something. So fascinating stuff, something for you to think about. But let's get back to our induction and motion. So what we have is the same magnetic force. We are going to practice Lenz's law again quickly. So what I want you to do is figure out the B induced here as this bar slides down, and the I induced, and the force on this bar. So go ahead and do that now. Okay, so once again, you could say, I don't need to do all that right-hand rule business. I know as this bar is going to fall, there has to be a backwards force. But if you wanted to figure that out from magnetism, you would see that as this bar is sliding down, we're gaining more and more flux coming out of the board like this. So B induced has to oppose that. It has to go into the board. And then that means that with B induced going this way, the I induced here has to go to the left from the right-hand rule, one of the right-hand rules. And then from the other right-hand rule, this one, instead of this one, we say current, magnetic field, my three fingers, current, magnetic field, thumb, force on the bar upward. And the other force that acts on this bar is, of course, the force of gravity. which pulls the bar down and accelerates it while this is trying to hold it back. All right, so the 4 steps. Do you remember them? Make a differential equations. This time we're going to use Newton's laws. Separate the variables, integrate both sides, solve. So this time it's more convenient for me to make the differential equation as ma equals f net instead of a equals f net over m. Same equation, I just move the m to the other side with acceleration. Now, what are the forces? We've got force of gravity pulling this down in the forward direction and magnetic force in the backwards direction. So then I'm going to fill in the pieces that the acceleration is the derivative of velocity with respect to time. Now we've got a differential equation of an equation that defines the derivative of the function, and I have to go back and find what the original function was. So of course, force of gravity is mg, and then this backwards force minus, there it is, the magnetic force in the backward direction. Now I have to separate separate the variables. So what I'm going to do is find a common denominator on this side by multiplying by r over r, and that makes 1 fraction, which will allow me to divide by this entire numerator to bring this v on the same side as this dv. So this, you notice, ends up in the denominator on this side. The m is going to go with the r on this side, and the dt is going to multiply to the other side. So I divided by this and then moved these over to this side, and that gave me that. The next step, so I've separated the separated variables, and now I'm going to integrate both sides. So I integrate from 0, because I let this bar go and it accelerates, to some final velocity, and our experiment begins at time 0, ends at some final time. The left side integrates to the natural log. I have dv over v, but if you don't see this term here, you would have to do a u substitution. I'm not going to do it. There's enough notes here for today. So basically, because this term, if we had just dv over v, it'd be log, but because of this term in front, we get a 1 over this term with a minus sign. And over our limits, this side's easy to integrate. 0 to t final, dt integrates to t from 0 to t final. So I integrated both sides. Last step, plug in the limits and solve for, what am I solving for? The velocity. So I plug in v final into this function. Oh, by the way, I moved these constants over to the other side with here. So I don't know if you could see this side. I brought the b squared L squared and the minus sign right there with the t final minus t initial. And on this side, I plug in v final right here and then 0 right here. So when I plug in v final, we have basically this expression again. But when I plug in 0, then we have just the log of this RMG. And on this side, the t and t final. So let me create a pause to allow you to catch up with these notes. Okay, so moving on. Now, again, I'm solving for v final. So I'm going to combine these two natural logs into one log. Because we have a subtraction, we combine them with a fraction. And then on this side, I just dropped the t final just to make it a little clearer. How do I get rid of the log to solve for v final? I use the exponential function. Exponential to this gets rid of the log, and exponential to this. So both sides into the exponential function. And then I also simplified by separating this fraction up. This over this is 1, and then this over this gives me this expression. So I'm going to move the exponential with the 1, and then move all this to this side. And then the last thing, multiply all the constants over, and I have my final velocity right here. That 1 minus exponential. This bar begins at rest, so if we had a velocity graph, I'll show you in a minute, it goes up and asymptotically approaches this final value, which is what we call the terminal velocity. If this bar has a long way to fall, eventually it reaches a top speed where the gravity force and the magnetic force balance. By the way, if we wanted just a terminal velocity, we didn't have to go through all of this. We could have just gone right here and set 0 equals, or Fg equals Fb, these two, and solve for V, and we would have gotten that expression without all that nice math, but a lot less effort. So let me create a pause, let you catch up with the notes. Last thing that I want to do is graph this function. Maybe what I'll do is I'll just erase this here because I don't want to erase any of the solution. So I set up some axes, time like this, and then our function, our velocity approaches this term in the front as our terminal velocity. And then this is velocity axis, and this goes, well, that 1 minus exponential that approaches that value. So there's a plot of the velocity with respect to time. So go ahead and copy that graph down as well. All right, so that was motion of an object because of inductive forces. Case 1 was when we projected something and we let the magnetic force slow it down with an exponential function. And in this case, we let the bar go, let gravity accelerate while we have a magnetic force in the backwards direction. In both cases, we follow 4 big steps. Make a differential equation using Newton's laws. Separate the variables, all velocity on one term, all time on the other. Integrate both sides and solve for the velocity. So that's it for today. I hope you enjoyed the physics. I hope you enjoyed the video. Hope you enjoyed another round of differential equations. Always fun. I'll see you in the next physics video.